Hello there and welcome back to the Science Sleepy Minds. Tonight, you're standing barefoot on a slab of rock that is older than anything your brain was designed to comprehend. Feel the cool surface under your toes. That stone beneath you has been here for billions of years, pressed and folded and heated and cooled, long before the first tree, long before the first fish dragged itself onto a muddy shore, long before anything with eyes existed to look up at the stars. And tonight you're going to ask a question so enormous it might make the ground feel a little less solid. What if human beings are not the first civilization this planet has ever produced? What if something else was here before us, lived, built, thought, and vanished so completely that we have no idea it ever existed? That thought alone is enough to make your pillow feel a little heavier. You probably will not survive this one with your sense of cosmic importance intact. And honestly, that is part of the fun. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop a comment and tell me where you're listening from tonight and what time it is where you are. I always love reading those. Someone is always tuning in from a time zone I forget exists. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You press your palm flat against that ancient stone, and you try to feel something, some vibration, some whisper from whatever came before. Of course, the rock gives you nothing. It never does. Rocks are famously tight-lipped. But the silence is exactly the problem, because silence in the geological record does not mean nothing happened. It might just mean that the evidence has been swallowed, recycled, ground into dust, and stirred back into the planet's molten interior like sugar dissolving in hot tea. Let that image settle for a moment. You're lying in the dark, breathing slowly, and you're about to take a walk through deep time. Not the kind of deep time you learned about in school, where a teacher rattled off a few dates and pointed at a poster of dinosaurs. This is the real thing. The kind of deep time that makes 4,000 years of recorded human history look like the last letter of the last word on the last page of a very, very long novel. The kind of deep time where entire mountain ranges rise and erode to nothing and rise again, where oceans open and close like slow-motion breathing, where continents drift around the globe like lazy guests at a party who cannot decide where to sit. You start by trying to get a feel for just how old this planet actually is. Earth formed roughly 4.5 billion years ago. You've heard that number before, probably nodded at it, maybe even wrote it on an exam once. But hearing it and understanding it are two very different things. Your brain evolved to track seasons, to count the days until a fruit ripens or a predator returns. It did not evolve to genuinely grasp 4.5 billion years. So let us try a little exercise. Imagine that the entire history of Earth is compressed into a single 24-hour clock. You start the clock at midnight, and the planet forms in a blaze of molten rock and cosmic debris. For the first several hours, nothing much happens that you would recognize. The surface is a hellscape of lava and asteroid impacts. The oceans begin to appear maybe around 4 in the morning. The earliest hints of microbial life show up not long after, maybe by sunrise, though historians and biologists still argue whether those earliest fossils are genuine biological signatures or just oddly shaped minerals playing tricks. For most of the morning and the entire afternoon, life is nothing but single-celled organisms, tiny blobs drifting in ancient seas. No drama, no plot, just chemistry doing chemistry in warm water for hour after hour. Complex multicellular life does not really get going until somewhere around 8 or 9 in the evening. Dinosaurs show up around 11 at night. They dominate for roughly 45 minutes of clock time, which in reality is about 165 million years. And then they're gone, swept away by an asteroid on a very bad day. Mammals rise, primates evolve, and modern human civilization, Everything from the invention of agriculture to this very moment occupies roughly the last fraction of a second before midnight. 1 fraction of a second. That is you. That is all of recorded human history. Every empire, every cathedral, every war, every love poem, every rocket launch. A blink so brief that if you were watching the clock you would miss it entirely. And here is the thought that should make your eyelids feel just a little heavier tonight. Look at all those hours that came before, all those long, silent stretches of morning and afternoon and evening. Hours and hours and hours of time in which the planet was alive, churning, evolving, experimenting. Is it really so impossible that somewhere in that vast expanse, something else arose? Something curious, something clever, something that looked up at the sky and wondered what was out there, just like you are doing right now. The mainstream scientific position, and you should know this up front because honesty matters even in a sleepy narration, is that there is no confirmed evidence of any pre-human civilization on Earth. None. Zero. The fossil record, incomplete as it is, has not handed us a Precambrian smartphone or a Devonian highway. But the absence of evidence, as the old saying goes, is not evidence of absence. And a growing number of scientists, not fringe theorists wearing tinfoil hats, but actual published researchers with university offices and coffee-stained desks, have started asking whether we have been looking at this question the wrong way. Whether the very tools we use to study the past might be fundamentally incapable of detecting what we are looking for. That is the thread you're going to follow tonight. Not a conspiracy theory, not ancient aliens, just a calm, honest, slightly unsettling scientific question. If a civilization existed on Earth, millions of years before us, would we even know? You pull the blanket a little higher, the fan hums, and somewhere deep beneath you, the Earth keeps its secrets packed tight in layers of stone and silence and time. You let that fraction of a second image linger for a moment, the way a last sip of tea holds its warmth on your tongue. Your entire species, everything you have ever known, compressed into a sliver of time so thin it barely registers on the cosmic clock. And now you start to stretch backward, letting your mind unspool into the hours and hours that came before that final tick. 4.5 billion years. You already know the number, but now you want to feel it in your bones. So you try another trick. Imagine you could walk backward through time at a pace of 1 year per step. Just a normal walking stride, about 3 feet, and every step carries you 1 year deeper into the past. To reach the time of Julius Caesar, you would walk about 2,000 steps. That is a leisurely stroll down a quiet street. Maybe 15 minutes of walking. To reach the construction of the Great Pyramid at Giza, roughly 4,500 steps. Still not even a serious hike. You could do it before lunch and still have time for a sandwich. But to reach the extinction of the dinosaurs, you would need to walk 66 million steps. At a comfortable pace, that journey would take you roughly 3 years of non-stop walking, no sleeping, no stopping for snacks, just 1 foot in front of the other for 3 straight years. And to reach the formation of Earth itself, you would need to walk for over 70 years without pausing. You would start as a young adult and arrive as an elderly person who has done nothing their entire life, but take 1 step per second into the past. That is the scale you're dealing with tonight. And the uncomfortable part, the part that should make your pillow feel like it is slowly pulling you deeper, is that modern humans have only been around for about 300,000 of those years. Anatomically modern humans, meaning people who looked like you and could theoretically sit next to you on a bus without anyone noticing, have existed for a sliver of time so narrow that on your walking timeline it would be about a 4-minute stroll. Recorded civilization, the part with writing and cities and taxes, is roughly 5,000 years. That is a walk across your living room. Now you look back at the rest of that 70-year march and you notice something obvious and slightly dizzying. Most of it is empty. Not empty of life, because life has been around for nearly 4 billion years in some form, but empty of anything you would recognize as intelligent. At least that is what the textbooks say. The official story is that complex intelligence is a recent invention, a quirky trick that evolution stumbled upon only in the last few million years with the rise of primates and eventually humans. Before that, according to the standard narrative, Earth was a planet of bacteria, then fish, then reptiles, then mammals, but never a planet of thinkers. And for a long time, nobody seriously questioned that story. Why would they? The evidence seems straightforward. You dig into old rock, you find fossils of ancient creatures, you see a general trend from simple to complex, and you note that nothing resembling a city or a tool shows up until very recently. Case closed. Humans are the first and only civilization. Pop the champagne and feel special. But here is where the quiet doubt creeps in, the kind of doubt that sneaks up on you at 2 a.m. when the house is still and the world feels too large. The fossil record, that supposedly straightforward ledger of ancient life, is not actually straightforward at all. It is riddled with gaps, enormous, yawning, canyon-sized gaps where millions of years pass with almost no preserved evidence whatsoever. Paleontologists have a name for this problem. They call it the incompleteness of the fossil record, which is a polite way of saying that the story of life on Earth is a book with most of its pages ripped out. Consider this genuinely strange fact. Of all the species that have ever lived on Earth, scientists estimate that more than 99% have gone extinct. That number alone is staggering. But here is the kicker. Of that 99%, the vast majority left no fossils at all. None. They lived, they reproduced, they filled ecological niches for millions of years, and then they vanished without leaving a single trace in the rock. Scholars still argue whether the true percentage of species preserved as fossils is closer to 1% or 1/10 of 1%, and some estimates push it even lower. You're essentially trying to read a library where almost every book has been burned, and the remaining few are water damaged and missing their covers. The reason for this is simple and a little bit cruel. Fossilization requires a very specific set of conditions. An organism needs to die in the right place, usually in or near water, get buried quickly under fine sediment before scavengers and bacteria destroy it completely, and then remain undisturbed for millions of years while minerals slowly replace its tissues. If any single step in that chain fails, no fossil, the creature simply disappears. Soft-bodied organisms, things without bones or shells, almost never fossilize. Entire ecosystems of jellyfish and worms and soft-shelled creatures lived and died for hundreds of millions of years and left virtually nothing behind. The famous Burgess Shale in British Columbia, which preserved an extraordinary snapshot of soft-bodied Cambrian life, is considered remarkable precisely because that kind of preservation almost never happens. It is a fluke, a geological accident, a 1 in a million postcard from 500 million years ago. And if entire species of large, abundant, long-lived animals can vanish without a fossil trace, what chance would the artifacts of a civilization have? You're not talking about bones now. You're talking about buildings, roads, tools, machines, things made of materials that weather and corrode and crumble, things that would need to survive not just thousands of years, but tens of millions, possibly hundreds of millions. The stone beneath your back suddenly feels less like a floor and more like a mouth that has swallowed everything that came before you and left no crumbs. You breathe out slowly and let that thought settle. The planet is old. You are not. And the record of what happened before you arrived is full of holes large enough to hide almost anything. You are still lying there, feeling the weight of all those missing pages, and now, a new question floats up like a bubble from the bottom of a dark pond. If you're going to wonder whether some ancient civilization might have existed before humans, you first need to figure out what you even mean by the word civilization, because that word carries a lot of baggage, and most of it is packed by humans who are, understandably, a little biased toward their own experience. And when you hear civilization, your mind probably jumps to cities, skyscrapers, highways, libraries, parliaments, coffee shops with questionable Wi-Fi. You picture monuments and writing systems and currency and sprawling infrastructure. And that is fair, because that is the version of civilization you grew up inside. But here is the thing that makes this question so slippery and so interesting. That image of civilization is based entirely on what one species on one planet built over roughly the last 10,000 years. It is a sample size of 1, and in science, a sample size of 1 is not a conclusion. It is a starting point for a much humbler conversation. Think about it this way. If you had never seen a bird and someone described flight to you, you would probably imagine something with jet engines and metal wings. You would define flight by the only version of it you knew, and then you would walk outside and see a sparrow and realize that flight can look completely different from anything you imagined. The same logic applies to civilization. You define it by the only example you have, but that does not mean every civilization must look like yours. It does not need skyscrapers. It does not need the internet. It does not even need fire, though fire is admittedly very useful for making toast. Scientists who study this question, and there are more of them than you might expect, tend to use a broader and more flexible definition. At its core, a civilization is usually described as a sustained collective enterprise by intelligent organisms that significantly modifies their environment. That is it. No requirement for wheels or alphabets or tax codes, just a group of smart beings working together in ways that leave a mark on the world around them. By that definition, you could imagine a civilization of aquatic creatures that reshaped coral reefs into vast planned structures, or a civilization of social insects that engineered underground networks with ventilation and waste management far beyond what any current ant colony achieves, or something even stranger, something so unlike human experience that you would not recognize it as civilization even if you were standing in the middle of it. This is where the debate gets genuinely fascinating and a little bit heated. Some researchers argue that intelligence of the kind required for civilization is so rare and so dependent on a specific chain of evolutionary accidents that it has probably only happened once on Earth. They point to the fact that life existed for billions of years before anything resembling complex intelligence appeared. Clearly, they say, the universe is not in a hurry to produce thinkers. Intelligence is not inevitable. It is a fluke, a cosmic lottery ticket, and you should be grateful you won it rather than expecting others to have won it before you. But other researchers push back, and they push back hard. They point out that you are committing a logical error by assuming that the absence of evidence in the fossil record means evidence of absence. Just because you have not found signs of pre-human intelligence does not mean it did not exist. It might mean your detection methods are not up to the task. It might mean the evidence has been destroyed by the very geological processes that make Earth such a dynamic and livable planet. Scholars still argue whether the emergence of intelligence is a predictable outcome of evolution given enough time and the right conditions, or whether it is a genuine, one-off miracle that happened to occur in African primates a few million years ago. And there is a deeper philosophical knot here, one that is worth tugging at gently as you sink a little further into your mattress. The criteria you use to define civilization will determine what you are able to find. If you define civilization as a species that uses radio waves, you will look for radio signals. If you define it as a species that builds with stone, you will look for stone structures. But what if the ancient civilization you're imagining did not use radio waves or stone? What if it was based on biological engineering, manipulating living organisms to serve its needs the way you manipulate metal and silicon? What if its technology was organic, biodegradable, designed to dissolve back into the ecosystem after use? You would never find it. Not in 1,000,000 years. Not in 100 million. It would be invisible to every detection method you currently possess, and you would walk right over its remains without a flicker of suspicion. This is the trap of anthropocentrism, the very human habit of assuming that everything important in the universe must look like something humans would do. You search for civilizations that resemble your own, because those are the only ones you know how to recognize. And in doing so, you might be blinding yourself to evidence that is sitting right under your feet, woven into the chemistry of the soil, folded into the genetics of living organisms, hidden in patterns you have not yet learned to read. There is a wonderfully quirky thought experiment that a few biologists have floated over the years. What if the forests themselves are the ruins? Not the trees individually, but the intricate symbiotic networks that connect them underground. The fungal threads that allow trees to share nutrients and chemical signals across vast distances. What if those networks are not purely natural, but are the degraded remnants of something that was once deliberately engineered? It sounds wild, and it almost certainly is not true, but the fact that you cannot definitively rule it out tells you something important about the limits of your knowledge. You do not need to believe any of this to find it interesting. You just need to sit with the possibility that the word civilization might be bigger than you thought, that your definitions might be too narrow, that the universe might have tried this experiment more than once, in forms you have not imagined yet, and that the evidence might be hiding not because it does not exist, but because you have not yet figured out how to look. The fan hums, your breathing slows, and somewhere beneath the soil, beneath the rock, beneath the memory of every creature that ever lived, the question waits. That question keeps waiting, patient as stone, and in 2018, 2 scientists decided to drag it out of the philosophical shadows and into the light of genuine academic inquiry. Their names are Gavin Schmidt and Adam Frank. Schmidt is a climate scientist at NASA, the kind of person who spends his days modelling the atmosphere of an entire planet, and Frank is an astrophysicist at the University of Rochester, the kind of person who spends his days thinking about what might be happening on other entire planets. Together they published a paper that asked a deceptively simple question, and gave it a name that makes it sound like it belongs in a science fiction novel. They called it the Silurian Hypothesis. Now before you get excited, the name is a joke, a deliberate, nerdy, slightly mischievous joke. It comes from a classic episode of the British television show Doctor Who, in which an ancient race of intelligent reptiles called the Silurians is discovered living beneath the Earth's surface, having built a civilization long before mammals took over. Schmidt and Frank borrowed the name with a wink, fully aware that it would make their paper memorable and slightly controversial. Scientists are allowed to have fun sometimes, even when the question they're asking is deadly serious. And the question is this: if an industrial civilization had existed on Earth tens of millions of years before humans, what evidence would remain today, and would we even know how to detect it? Not a thought experiment about alien visitors, not a conspiracy theory about Atlantis or Lemuria, a straightforward scientific inquiry about what the geological record can and cannot preserve over deep time. You might assume the answer is obvious. Of course we would find something. Cities leave rubble, factories leave pollution, mines leave scars. An industrial civilization would be impossible to miss. But Schmidt and Frank walk you through the logic with the calm patience of people who have done the math, and the math is not reassuring. Start with the most durable things humans have built: concrete, steel, glass, asphalt. These feel permanent to you because your frame of reference is a human lifetime. maybe a few centuries at most. You look at Roman roads still visible after 2,000 years and you think, well, clearly our stuff lasts. But 2,000 years is nothing. It is a rounding error in geological time. Stretch your timeline to 10 million years and every Roman road is dust. Every skyscraper is a faint chemical smudge in a layer of sediment. Every glass window has devitrified, broken down into a grainy crystalline residue that looks like ordinary sand. Steel has rusted into iron oxide and been absorbed back into the mineral matrix of the surrounding rock. Concrete has crumbled, dissolved, and been carried away by groundwater. The physical structure of a city simply does not survive that kind of time, and 10 million years is actually a short window for this thought experiment. Schmidt and Frank are asking about timescales of 50 million, 100 million, even several hundred million years. At those depths, plate tectonics has reshaped the surface of the planet. Continents have drifted thousands of miles. Mountain ranges have risen and eroded to plains. Ocean floors have been swallowed into the mantle and replaced with fresh basalt. The very ground on which a civilization might have stood has been recycled, melted and reformed into something unrecognizable. It is like trying to find a message written on a sheet of paper that has been shredded, soaked, pulped, and pressed into a new sheet. The message is gone. The paper itself is gone. Only the atoms remain, rearranged into something that remembers nothing. So if the physical artifacts are hopeless, what about the chemical signatures? This is where Schmidt and Frank's paper gets genuinely interesting, because while buildings crumble, chemistry lingers. An industrial civilization would burn fossil fuels, and burning fossil fuels changes the ratio of carbon isotopes in the atmosphere. Specifically, it increases the amount of the lighter carbon-12 relative to the heavier carbon-13, because fossil fuels are derived from ancient biological material that preferentially incorporated the lighter isotope. That shift gets recorded in ocean sediments, in limestone, in the shells of tiny marine organisms called foraminifera that drift to the sea floor when they die. If you drill a core of ocean sediment and analyse the carbon isotope ratios layer by layer, you are reading a chemical diary of the atmosphere stretching back millions of years. And here is the part that made a lot of people sit up a little straighter when they read the paper. There are, in fact, several anomalous carbon isotope excursions in the geological record. Moments where the carbon ratios shift dramatically in ways that are not fully explained by known natural processes. Scholars still argue whether these excursions are entirely attributable to volcanic activity, methane releases from the ocean floor or other geological mechanisms, or whether something else might be contributing. Nobody is claiming these anomalies prove a pre-human civilization existed. That would be an extraordinary leap far beyond what the data supports. But the anomalies do demonstrate that the kind of signal an industrial civilization would leave behind is exactly the kind of signal that could be confused with natural geological events. That is the real sting of the Silurian hypothesis. It is not that we have evidence of a prior civilization. It is that we might not be able to tell the difference between evidence of a prior civilization and the ordinary background noise of a geologically active planet. The signal and the noise look the same, and if they look the same, you cannot rule the hypothesis out. You can only shrug, note the uncertainty, and keep looking. There is a wonderfully dry moment in Schmidt and Frank's paper where they essentially admit that the hypothesis is almost impossible to falsify, which in scientific terms is a polite way of saying it sits right on the boundary between productive inquiry and an unanswerable riddle. They're not trying to prove that ancient civilizations existed. They're trying to prove that the question is worth asking, that the tools we use to study the deep past have blind spots large enough to hide an entire world. You lie there and let that idea wash over you like a slow tide. The planet you live on might be keeping secrets, not because it is malicious, but because it is old, and old things forget. The fan hums its single patient note, and somewhere in a lab, a scientist is slicing open a core of ancient mud, reading the chemistry of a world that no longer exists, wondering if the numbers are trying to tell a story that nobody alive knows how to hear. That scientist with the mud core is looking at one of the most humbling puzzles in all of geology, and tonight you are going to sit with it for a while. Because the deeper you go into this question, the more you realise that the fossil record, the thing you were taught in school to think of as the definitive history of life on Earth, is less like a detailed biography and more like a handful of postcards found in the attic of a house that has burned down 3 times. You already know that fossilization is rare. You touched on that a few minutes ago when you learned that more than 99% of all species left no trace. But now you want to understand just how selective and how misleading that rarity can be. Because the fossil record does not just lose information randomly, like a sieve that lets everything through equally. It loses information in patterns. It has biases. It preferentially preserves certain kinds of organisms in certain kinds of environments and quietly forgets everything else. And those biases are exactly the kind of thing that could hide evidence of intelligence if intelligence ever arose in the wrong body in the wrong habitat at the wrong time. Let us start with the body problem. Fossils overwhelmingly favour organisms with hard parts. Bones, teeth, shells, exoskeletons. If you had a skeleton made of calcium phosphate or a shell made of calcium carbonate, congratulations. You had a decent shot at being remembered by the future. But if you were soft-bodied, if your entire physical structure was muscle and skin and cartilage and flexible tissue, your chances of fossilization dropped to nearly 0. Sharks have been swimming the oceans for over 400 million years, and yet their fossil record is almost entirely teeth. Teeth and the occasional vertebra. The rest of the body, the muscle, the cartilage, the skin, the brain, all of it dissolved back into the ocean and vanished. 400 million years of sharks, and almost all you have to show for it is a scattering of teeth in sedimentary rock. If sharks can barely leave a trace, imagine what happened to the octopus lineage, which has no hard parts at all. No bones, no shell, no teeth worth preserving. Octopuses are among the most intelligent creatures on the planet, and their fossil record is so thin it could fit in a small drawer. Scholars still argue about the evolutionary timeline of cephalopod intelligence precisely because the physical evidence is so sparse that every new fossil discovery reshuffles the whole picture. Now layer on the habitat problem. Fossilization favours aquatic and semi-aquatic environments, places where sediment can bury a body quickly before decomposition destroys it. River deltas, shallow seas, lake beds, floodplains. If you lived and died in a dense forest, on a mountaintop, in a dry grassland, or in any environment where your body was exposed to air, scavengers, and bacterial decay, you are almost certainly not going to fossilize. This means the fossil record is heavily skewed towards certain ecosystems and almost blind to others. Entire biomes, teeming with life for millions of years, might be represented by a handful of fragments or nothing at all. And here is a quirky little detail that paleontologists love to share at dinner parties, assuming they get invited to dinner parties, which frankly they deserve to be. There is a phenomenon called the senior lips effect, named after the 2 scientists who formalized it, which describes how the apparent last appearance of a species in the fossil record almost never corresponds to its actual extinction. Because fossilization is so rare and so patchy, the last fossil of a species is almost always much older than the last living member of that species. The species keeps existing for thousands or millions of years after its last fossil, like a guest who has already left the party, but whose coat is still hanging by the door. This means the fossil record systematically makes extinctions look earlier than they actually were, stretching out the apparent gaps between one group's disappearance and another's arrival. Now take all of these biases and distortions and stack them on top of each other, and you start to see the scale of the problem for anyone trying to detect a pre-human civilization. You are looking for evidence of intelligence, which is a behavioural trait, not a physical one. Intelligence does not fossilise. A big brain might leave behind a large skull, but a clever organism that solves problems, communicates, manipulates its environment, and builds things does not necessarily have a big skull. It might be soft-bodied. It might live in an environment hostile to preservation. It might build with biodegradable materials that dissolve within centuries, let alone millions of years. Every bias in the fossil record works against you. There is a famous analogy that one paleontologist used, and it goes something like this. Imagine you are trying to reconstruct the history of New York City using only the information that would survive being buried under a mile of sediment for 50 million years. The skyscrapers are gone, the subway tunnels have collapsed and filled with rock, the asphalt has broken down, the plastic has degraded into microscopic polymer fragments scattered through the surrounding soil. The paper, the wood, the fabric, the food, the people, all gone. What remains? Perhaps a thin layer of unusual chemical concentrations, a slight anomaly in the carbon isotopes, a scattering of synthetic molecules that do not occur naturally, a faint trace of heavy metals from industrial processes. If you were a geologist 50 million years from now, drilling a core through the sediment of what was once Manhattan, you would find a weird blip in your data. You might note it. You might write a footnote about an unusual geochemical excursion in the mid-Cenozoic, and then you would move on because a weird blip is not proof of anything. It is just a weird blip. That is the fossil record's gift and its curse. It tells you just enough to make you curious and never quite enough to give you a definitive answer. You are reading a story written in disappearing ink, and the parts that remain might not be the parts that mattered most. You shift slightly under your blanket. The darkness feels thicker now, heavier, like it is full of all the things the Earth decided not to remember. And you're only just getting started. You're thinking about that buried Manhattan now, that thin, weird blip in a future geologist's data, and the question forms itself almost lazily in your settling mind. Forget about fossils for a moment. Forget about bones and teeth and shells. What about the actual stuff a civilization builds? The hard, heavy, engineered materials that feel so permanent when you walk past them every day. Could ruins survive deep time? Could a building, a bridge, a highway, a dam make it through 10 million years? 100 million? Could anything you have ever built outlast the patient grinding of a planet that has all the time in the world? The short answer is no. The longer answer is a slow, detailed, slightly melancholy no that is worth walking through, because it teaches you something profound about the impermanence of everything humans consider durable. Start with steel, the backbone of modern construction. Steel is an alloy of iron and carbon, and iron really, really wants to become iron oxide. You know iron oxide by its common name, rust. In the presence of oxygen and water, which are two things Earth has in abundance, steel corrodes steadily and relentlessly. A steel beam exposed to the elements will lose structural integrity within decades. Buried underground, protected from direct weathering, it lasts longer, but not the kind of longer that matters here. Within a few thousand years, most steel structures have corroded into brittle, flaky masses of rust. Within 100,000 years, those masses have broken down further into iron-rich mineral deposits, indistinguishable from natural iron formations. Give it 1,000,000 years, and there is nothing left that a geologist would recognize as artificial. The steel has gone home. It has returned to the ore it came from, and the Earth has reclaimed it without so much as a receipt. Concrete fares a little better, but only a little. Roman concrete, the famous stuff that has lasted 2,000 years and inspired countless breathless articles about how the Romans were better engineers than we are. survives because of a specific chemical reaction involving seawater and volcanic ash that creates a self-healing mineral structure. Modern Portland cement does not have this property and degrades faster. But even Roman concrete, given enough time, succumbs. Water seeps into cracks, freezes, expands, and splits the material apart. Chemical reactions with groundwater dissolve the calcium compounds. Biological activity, roots and burrowing organisms, breaks the structure into fragments. Over 1 million years, a concrete building is rubble. Over 10 million years, that rubble has been chemically altered, compressed, and folded into the surrounding sediment until it is just another layer of calcium-rich rock. You might notice a slightly unusual mineral composition if you happen to drill through it, but you would probably chalk it up to a natural limestone formation and keep drilling. Glass is interesting because it is technically already a mineral, a disordered amorphous solid made primarily of silicon dioxide. In theory, silicon dioxide is extremely stable. In practice, glass devitrifies over geological time, meaning its disordered structure slowly reorganizes into a crystalline form. The glass becomes cloudy, then grainy, then indistinguishable from quartz sand. Natural volcanic glass, obsidian, undergoes this same process, and geologists know that obsidian older than a few million years is exceptionally rare because it has all converted to other mineral forms. Your windows, your bottles, your phone screen, all of it would become sand given enough patience, and the Earth has nothing if not patience. And then there is plastic, the material that everyone assumes will last forever because of those depressing photographs of sea turtles tangled in grocery bags. Plastic does persist for a long time by human standards, potentially thousands of years in the right conditions, but deep time laughs at thousands of years. Ultraviolet radiation breaks plastic down into smaller and smaller polymer fragments. Microbial activity, which scientists have only recently discovered can actually digest certain plastics, further degrades the material. Heat and pressure from burial accelerate chemical decomposition. Over 1 million years, your plastic is reduced to a diffuse scatter of synthetic polymer molecules distributed through the sediment. Scholars still argue whether these microplastic signatures would remain detectable after 10 million years, or whether they would eventually break down into their constituent carbon and hydrogen atoms and vanish entirely. The honest answer is that nobody knows for certain, because nobody has ever had to look for 10-million-year-old plastic before. It is a question that did not need asking until someone like Schmidt and Frank came along and ruined everyone's sense of security. So here you are, mentally watching an entire city dissolve. The skyscrapers rust and crumble, the concrete splits and dissolves, the glass becomes sand, the plastic fragments into molecular dust. The roads buckle, crack, and are swallowed by vegetation, and then by sediment, and then by the slow churn of geological processes that do not care what you built or why you built it. Within a few million years, the physical footprint of a city is gone. Not hidden, not buried, gone, reabsorbed into the planet like a sugar cube in a warm bath. There is a wonderfully humbling thought experiment that the science writer Alan Weisman explored in his book about what would happen if humans vanished overnight. Within 2 days, the New York subway system floods. Within 20 years, most streets are rivers of grass and saplings. Within a few hundred years, most structures have collapsed. Within a few thousand years, the only things still standing are a few stone monuments and some stainless steel underground vaults, and even those are on borrowed time. The planet does not mourn your architecture. It simply moves in, takes over, and redecorates. And if that is what happens to a civilization at the peak of its technological power, imagine what happens to one that existed 50 million years ago, or 100 million, or 300 million. Imagine a civilization that built with wood instead of steel, or with biological materials you have no name for, or with technologies that left no physical structure at all. The planet would not just erase that civilization, it would erase the erasure. There would be no gap, no void, no suspicious absence in the record, just smooth, continuous rock, telling a story that conveniently leaves out the most interesting chapter. You breathe in slowly, you breathe out, the fan turns, and the ground beneath you holds its silence. But the ground is not perfectly silent, not if you know how to listen with the right instruments. Because even though buildings crumble and steel rusts and glass becomes sand, chemistry is more stubborn than architecture. Molecules are gossips. They talk long after the structures that produced them have been reduced to nothing. And if you know how to read their whispers in the layers of ancient rock, they might just tell you something extraordinary. This is the real frontier of the Silurian Hypothesis, the place where the question stops being a philosophical thought experiment and starts becoming something you could actually test. Physical ruins do not survive deep time. You have already made peace with that, but chemical signatures, isotopic ratios, trace elements, synthetic compounds, these can persist in sedimentary rock for tens of millions of years, sometimes hundreds of millions. They are the ghosts that linger after the body is gone, and a few of them are genuinely hard to explain. Start with carbon isotopes, because that is where Schmidt and Frank planted their flag. You already know the basic idea. Burning fossil fuels shifts the ratio of carbon-12 to carbon-13 in the atmosphere, because biological material is enriched in the lighter isotope. That shift gets recorded in ocean sediments, in carbonate rocks, in the tiny shells of foraminifera. An industrial civilization burning through millions of years of stored organic carbon would produce a sharp, sudden negative excursion in the carbon-13 record. A dip that would look like something dumped a lot of biologically derived carbon into the atmosphere in a geologically short period of time. And the geological record has several of these dips. They show up as sudden wobbles in isotope curves that scientists have been charting for decades. Most of them have been attributed to natural causes, massive volcanic eruptions that release carbon dioxide, sudden destabilization of methane hydrates on the ocean floor, large-scale die-offs of marine organisms. These explanations are well supported and widely accepted. Nobody is seriously proposing that every carbon anomaly in the rock record is evidence of an ancient factory. But the point Schmidt and Frank make, and it is a sharp one, is that the chemical fingerprint of an industrial civilization would look almost identical to the chemical fingerprint of certain natural geological events. You would see the same isotopic shifts, the same temperature changes, the same patterns of ocean acidification. Distinguishing one from the other would require a level of precision and a set of diagnostic tools that geologists have not yet fully developed. Beyond carbon, there are other chemical breadcrumbs that a civilization might leave behind. Nitrogen isotopes would shift if large-scale agriculture altered the nitrogen cycle through fertilizer use. Trace metals like lead, mercury, and cadmium would spike in sediment layers if industrial processes released them into the environment. In fact, there is a measurable lead spike in ice cores and sediments, corresponding to the Roman Empire's extensive lead smelting operations, a signal that is still detectable 2,000 years later. Now imagine an entire industrial economy running for centuries or millennia. The metal contamination signature could potentially survive millions of years, compressed into a thin but anomalous layer of enriched sediment. And then there are synthetic molecules, compounds that do not exist in nature and can only be produced by deliberate chemical engineering. Modern human civilization has produced tens of thousands of these, from chlorofluorocarbons to certain pesticides to long-chain fluorinated compounds, sometimes called forever chemicals, because of their resistance to natural degradation. If any of these molecules, or their degradation products, were found in a sediment layer 50 million years old, it would be nearly impossible to explain through natural processes. That would be the smoking gun, the one piece of evidence that could distinguish an industrial civilization from a volcanic eruption or a methane belch. Nobody has found that smoking gun. Let that be very clear, because honesty is the backbone of this entire conversation, and without it, you're just telling bedtime fairy tales. No confirmed synthetic molecules of unexplained origin have been identified in ancient sediments. No anomalous metal spikes that definitively point to industrial activity rather than natural processes. The chemical record, like the fossil record, has not handed us proof, but it has handed us some genuinely strange puzzles. There are layers of unusual mineral concentrations in certain rock formations that do not quite fit the standard explanations. There are deposits of natural nuclear reactors in Gabon, Africa, at a site called Oklo, where uranium ore spontaneously sustained nuclear fission reactions about 2 billion years ago. These are entirely natural, the product of specific geological and chemical conditions that happen to come together in just the right way. Scholars still argue about the full range of conditions that made the Oklo reactors possible, and while nobody credible claims they were engineered, they serve as a fascinating reminder that nature can produce phenomena that look astonishingly like technology. The line between natural and artificial is not always as crisp as you might like it to be. There is also the curious case of certain fullerenes, soccer ball-shaped carbon molecules, found in geological deposits that are hundreds of millions of years old. Some of these fullerenes contain trapped noble gases with isotopic ratios that are unusual for Earth, which led to a brief flurry of speculation about extraterrestrial or artificial origins. The current consensus is that these fullerenes formed naturally, possibly from carbon-rich materials subjected to intense heat and pressure during asteroid impacts. But the initial confusion illustrates the core problem beautifully. When you find something chemically weird in old rock, your first instinct is to find a natural explanation, and you usually can. The natural explanation is almost always correct, but the process of explaining away anomalies also means that a genuine artificial signal could be dismissed as natural noise before anyone thought to investigate it further. You're beginning to see the shape of the problem now. It's not that the evidence is there and being ignored. It is that the evidence, if it ever existed, would be so degraded and so ambiguous after millions of years that it would blend into the background hum of ordinary geology. You would need to know exactly what to look for and exactly where to look, and right now you're not sure you know either of those things. The fan hums, the dark wraps around you, and somewhere deep in the rock the chemistry waits to be asked the right question. The right question might already have an address, and it is written in a layer of ancient clay about 56 million years old. You are drifting now into one of the strangest chapters of Earth's climatic history, a period that climate scientists find both fascinating and slightly terrifying, and that supporters of the Silurian Hypothesis find irresistibly suggestive. It is called the Paleocene-Eocene Thermal Maximum, or the PETM if you prefer your geological catastrophes abbreviated, and it's the closest thing the deep past offers to a mirror of what industrial civilization does to a planet. Picture the Earth 56 million years ago. The dinosaurs have been gone for about 10 million years. Mammals are diversifying rapidly, filling the ecological niches left behind by the great reptiles. The planet is already warm by modern standards, with no ice caps at either pole, palm trees growing in what is now Wyoming, and crocodile relatives lounging in the Arctic. It is a greenhouse world, lush and humid and a little alien. And then, over a geologically brief period that scientists estimate at somewhere between a few thousand and 20,000 years, the temperature spikes. Global average temperatures jump by 5 to 8 degrees Celsius on top of an already warm baseline. The oceans acidify, marine species die in waves. terrestrial ecosystems are thrown into chaos as climate zones shift faster than most organisms can migrate. The cause, according to the mainstream explanation, was a massive release of carbon into the atmosphere. Something dumped an enormous quantity of greenhouse gas into the air in a geologically short burst, triggering a runaway warming event that took the planet roughly 200,000 years to recover from. The carbon isotope record shows exactly the kind of sharp negative excursion you would expect from such a release. A sudden dip in carbon-13 that indicates a huge injection of biologically derived carbon. So far, so straightforward. A big carbon dump caused a big warming event. Case closed. Except that scientists have been arguing for decades about where the carbon actually came from, and the debate is not as settled as textbooks sometimes imply. The leading hypothesis is that warming ocean temperatures destabilized vast deposits of methane hydrates, frozen methane trapped in sediments on the ocean floor, releasing gigatons of methane into the atmosphere where it acted as a powerful greenhouse gas before oxidizing into carbon dioxide. This is a well-supported and widely accepted explanation, but there are problems with the numbers. Some researchers have argued that methane hydrates alone cannot account for the full volume of carbon released. The isotopic signature suggests a source that is lighter in carbon-13 than what methane hydrates alone would produce. Other candidates have been proposed, including massive volcanic eruptions associated with the opening of the North Atlantic, burning of organic-rich sediments by igneous intrusions, and even large-scale wildfires triggered by volcanic activity. Scholars still argue about the exact combination of factors that produced the PETM. It was probably not a single cause, but a cascade, a domino chain of feedback loops that amplified an initial carbon release into a full-blown planetary crisis. And within that cascade of uncertainty, the Silurian hypothesis finds its most provocative foothold. Because here is the thing that makes the PETM so interesting for this conversation. The chemical signature of the event, the carbon isotope excursion, the temperature spike, the ocean acidification, the extinction patterns, looks remarkably like what you would expect to see if an industrial civilization had burned through a planet's worth of fossil fuels in a few thousand years. The rate of carbon release, the isotopic composition, the global environmental consequences, all of it maps onto the kind of damage that heavy fossil fuel use would produce. Schmidt and Frank noted this explicitly in their paper. They were careful to say that they were not claiming the PETM was caused by an ancient civilization. They were saying that if an ancient civilization had caused something like the PETM, you would not be able to distinguish it from the natural explanations currently on the table. That is a subtle but devastating point. It does not tell you that something was there. It tells you that you could not tell if something was there, which is a very different and in some ways more troubling conclusion. And there is a quirky little detail about the PETM that adds an extra layer of intrigue. Just before the main carbon isotope excursion, there is a smaller preliminary warming event that some researchers have interpreted as a precursor or trigger. It is as though something nudged the system before the main event, a gentle push that set the dominoes falling. In the natural explanation, this precursor is usually attributed to volcanic activity or a smaller initial methane release. But in the imaginative framework of the Silurian hypothesis, you could read it as the early stages of an industrial build-up, a civilization's growing carbon footprint before the full-scale burning began. You could read it that way. You probably should not, because reading geological data through the lens of what you want to find is a dangerous habit. But you could. The PETM also coincides with the dramatic reshuffling of mammalian evolution. Several new groups of mammals appear in the fossil record immediately after the event, including the earliest primates. Your distant ancestors emerge from the crucible of a global warming catastrophe that bears an uncomfortable resemblance to the one your current civilization is creating. There's a strange poetry in that, a loop in time that feels almost too neat, and you can let it settle into your mind like a stone sinking slowly into warm water. Nobody is building a career on the claim that the PETM was caused by an ancient industrial society. The evidence does not support that conclusion, and the natural explanations remain far more parsimonious and well evidenced. But the event serves as a perfect illustration of the core challenge. The geological record preserves outcomes, not causes. It shows you what happened to the planet, but not necessarily why. And when the outcome of a natural catastrophe looks identical to the outcome of industrial civilization, the record simply shrugs and offers you both possibilities with equal indifference. You turn your head slightly on the pillow. 56 million years is a long time ago, but the warmth of that ancient hothouse feels strangely close to night, as though the heat has been waiting patiently in the rock for someone to notice. That ancient warmth lingers as you drift further back now, much further, past the extinction of the dinosaurs, past the rise of flowers, past the breakup of supercontinents, all the way into a world so different from your own that it might as well be another planet. You're entering the Carboniferous period, roughly 300 to 360 million years ago, and the air here is thick with something you're not used to: oxygen, a lot of it. During the Carboniferous, atmospheric oxygen levels reach somewhere around 35%, compared to the 21% you breathe today. That might not sound like a dramatic difference, but it changed everything. Higher oxygen meant that biological processes could run hotter, faster, more efficiently. It meant that organisms could grow larger than anything you would consider reasonable. And the forests, the endless, sprawling forests of that era, were like nothing that has existed before or since. Imagine trees towering 100 feet tall, not oaks or maples or anything you would recognize, but giant club mosses and horsetails and tree ferns, primitive plants that today survive only as small ground-covering species, but in the Carboniferous grew into giants. The forests were so dense and so productive that dead plant material accumulated faster than bacteria and fungi could decompose it. This was partly because the microorganisms that break down lignin, the tough structural polymer in wood, had not yet fully evolved the enzymes to do the job efficiently. So dead trees piled up, layer after layer, century after century, compressed and buried and slowly transformed into the coal deposits that your own civilization would dig up hundreds of millions of years later and burn for energy. The Carboniferous literally means coal-bearing. The period is named after the fuel it left behind for you, and in this world of towering forests and oxygen-rich air, something remarkable was happening to the animals. Arthropods, the group that includes insects, spiders and crustaceans, grew to sizes that would make you deeply uncomfortable if you encountered them in your backyard. Dragonflies with wingspans of over 2 feet cruised through the canopy. Millipedes stretched to nearly 8 feet in length, longer than most humans are tall. Scorpions the size of dogs scuttled through the undergrowth. The high oxygen levels allowed these creatures to grow far beyond the limits that constrain their modern descendants, because arthropods breathe through a passive system of tubes called tracheae that deliver oxygen directly to their tissues, and higher oxygen concentrations mean those tubes can support a larger body. Now, nobody is suggesting that giant millipedes built libraries. That would be a stretch even for the most enthusiastic fringe theorist. But the Carboniferous raises a genuinely interesting question about the relationship between time, complexity, and intelligence. 300 million years is an almost incomprehensible span. Modern humans went from sharpening rocks to landing on the moon in roughly 2 million years, depending on where you start counting. The Carboniferous period alone lasted about 60 million years, 30 times longer than the entire history of the human genus. and the arthropods of that era were not simple creatures. They had sophisticated sensory systems, complex behaviours, social structures in some cases, and nervous systems capable of processing information from their environment in ways that modern entomologists are still working to fully understand. Scholars still argue about the upper limits of arthropod intelligence, both in the present and in the deep past. Modern honeybees can learn abstract concepts, navigate by mental maps, and communicate the location of food sources through symbolic dance. Modern octopuses, though not arthropods, demonstrate that invertebrate nervous systems can support problem-solving, tool use, and what some researchers cautiously describe as play. The assumption that intelligence requires a vertebrate body plan, a backbone, a skull, a big centralized brain is just that, an assumption. Evolution does not read your textbooks. It finds whatever solutions work, and it has had a very long time to experiment. Here is a quirky thought that a few speculative biologists have toyed with over the years. What if, during some forgotten stretch of the Carboniferous or the Permian that followed it, a lineage of arthropods or some other invertebrate group crossed an intelligence threshold? Not human-level intelligence necessarily, not language and philosophy and existential dread, but something functional, something that allowed coordinated environmental manipulation, collective problem-solving, maybe even rudimentary construction. An ant colony already does all of these things at a basic level. A termite mound is an engineered structure with climate control, ventilation, fungus farming, and waste management. Scale that up, give it 60 million years of evolutionary refinement in a world with extra oxygen and abundant resources, and where do you end up? You probably end up nowhere, because the evolutionary pressures that drive intelligence are specific and unpredictable, and do not simply scale with time. But the honest answer is that you do not know for certain where you end up, because the fossil record of that era is exactly the kind of incomplete, biased, hard part favouring record you spent the last few sections learning about. Soft-bodied organisms are ghosts in the Carboniferous. Behavioural complexity leaves no fossils. A civilization built from woven plant fibre and fungal cement would have decomposed within decades and left no trace in the rock. The giant dragonflies left you wing impressions in shale. The enormous millipedes left you trackways in sandstone. But neither of those things tells you what was happening inside those creatures' nervous systems any more than a footprint on a beach tells you what the person was thinking while they walked. You're left with shapes and shadows, outlines of bodies without any record of minds. The oxygen-rich air of the Carboniferous fades as you breathe your own modern 21% and feel it thin and ordinary in your lungs. 300 million years, 60 million of them in a single period teeming with life you can barely imagine. And all you have is coal and footprints and the nagging feeling that the story is bigger than the evidence can hold. You're still breathing that thin modern air and thinking about the limits of what a body can tell you about a mind, and that thought carries you naturally toward the strangest brain on the planet today. Not the human brain, impressive as it is. Not the dolphin brain or the crow brain, though both deserve their own episodes. No, tonight you're thinking about the octopus, an animal so bizarrely intelligent that it seems like evolution's way of reminding you that your assumptions about how minds work are embarrassingly narrow. The octopus has approximately 500 million neurons, which puts it in the same range as a dog. But unlike a dog, or a human, or any vertebrate you've ever met, the octopus distributes most of its neurons outside its central brain. About 2/3 of an octopus's neurons are in its arms, which means each arm can taste, touch, and make decisions semi-independently from the central brain. An octopus does not just think with its head, it thinks with its entire body. It is as if you woke up one morning and discovered that your hands had opinions and your fingers could solve puzzles without consulting you first. And what those distributed neurons can do is remarkable. Octopuses solve mazes. They open child-proof containers, which is more than some adults can manage. They recognize individual human faces and behave differently toward people they like and people they do not. They have been observed carrying coconut shell halves across the ocean floor, assembling them into shelters when needed, which meets most scientific definitions of tool use. In laboratory settings, they have figured out how to unscrew jars from the inside, escape from sealed tanks, and in at least one famous case, systematically short-circuit a light fixture that was annoying them by squirting jets of water at it. That last detail is not directly relevant to the Silurian hypothesis, but it is too delightful to leave out. The octopus lineage is ancient. Cephalopods, the group that includes octopuses, squid and cuttlefish, have been around for at least 500 million years. The earlier cephalopods had external shells, like the nautilus that still survives today, and over time various lineages lost their shells and developed the soft, flexible bodies you see in modern octopuses. This evolutionary transition happened independently in multiple cephalopod groups, suggesting that there is something advantageous about being soft and clever, rather than armoured and simple. Scholars still argue about when exactly the intelligence you see in modern octopuses first arose, because as you already know, soft-bodied organisms leave almost no fossils. The oldest confirmed octopus fossil is roughly 300 million years old, but it is just a body impression, a faint outline in limestone. It tells you the shape was there, but nothing about the behaviour, the cognition, or the neural complexity. And here is where convergent evolution enters the picture and makes everything more interesting and more unsettling. Convergent evolution is the process by which unrelated organisms independently evolve similar features in response to similar environmental pressures. Eyes evolved independently at least 40 times across different animal lineages. Wings evolved separately in insects, pterosaurs, birds, and bats. Echolocation evolved independently in dolphins and bats. Nature has a habit of inventing the same solutions over and over, as if it is following a playbook that has certain favourite pages. Intelligence, it turns out, appears to be one of those favourite pages. Complex cognitive abilities have evolved independently in mammals, birds, and cephalopods, three groups that are separated by hundreds of millions of years of evolutionary history. A crow and an octopus share a common ancestor so far back that it was essentially a flatworm, yet both can use tools, solve multi-step problems, and demonstrate what looks an awful lot like curiosity. This pattern suggests that intelligence is not a freak accident that happened once in primates. It is a convergent solution, something that evolution returns to again and again when the conditions are right. And if intelligence is convergent, if the universe has a tendency to produce minds whenever the ecological opportunity arises, then the probability that it happened only once on a planet that has been teeming with life for 4 billion years starts to look less like a safe assumption and more like a comforting story you tell yourself, because the alternative is overwhelming. There is a wonderfully strange paper published a few years ago, not entirely serious but not entirely joking either, that pointed out certain peculiarities in the octopus genome. The octopus has an unusually large number of a type of genetic element called transposons, which are segments of DNA that can copy themselves and move around within the genome. Transposons are associated with genetic innovation and rapid evolution, and the octopus has more of them in its neural tissue than almost any other organism studied. The paper speculated with deliberate provocation about whether the octopus's genetic complexity might have origins that are not entirely conventional. It was a fringe idea dressed up in legitimate molecular biology, and mainstream scientists largely rolled their eyes. But the underlying data, the genuine strangeness of the octopus genome, is real and not yet fully explained. You do not need to believe that octopuses are secret aliens or the descendants of an ancient civilization to find this relevant. What matters for tonight's question is simpler and more profound. Nature has produced complex intelligence multiple times, in bodies that look nothing like yours, using neural architectures that are fundamentally different from anything in the vertebrate world. If intelligence is this flexible, this repeatable, this willing to emerge in unexpected forms, then the deep past becomes a much more interesting place, because you are no longer asking whether intelligence could have arisen before humans. You're asking how many times it might have arisen, in how many different bodies, in how many different eras, and how many of those experiments left no trace at all in the rock beneath your sleeping head. The octopus in its den shifts a tentacle, tastes the water, considers its options. 8 arms, 3 hearts, blue blood, and a mind that owes nothing to your evolutionary lineage. If intelligence can look like that, it can look like anything. And you're running out of reasons to assume you were first. You're running out of reasons, but the Earth has one more trick for hiding its secrets, and it is the most brutal one yet. You've been thinking about how fossils fail and chemistry fades and ruins crumble, all the gentle, patient ways the planet erases evidence over millions of years. But sometimes the planet does not bother with patience. Sometimes it just sets the world on fire and starts over. You're entering the Permian extinction, the single worst catastrophe in the history of complex life on Earth, and if anything could swallow a civilization whole without leaving a trace, this is it. It happened roughly 252 million years ago, at the boundary between the Permian and Triassic periods, and the numbers are so staggering that they almost stop meaning anything. Approximately 90 to 96% of all marine species went extinct. Around 70% of terrestrial vertebrate species vanished. Insects, which are famously resilient and had survived every previous crisis with barely a shrug, suffered their only known mass extinction in their entire evolutionary history. The oceans turned anoxic, meaning they lost most of their dissolved oxygen and became hostile to almost everything that lived in them. The atmosphere filled with carbon dioxide and possibly hydrogen sulfide, a toxic gas that smells like rotten eggs and kills most animals in high concentrations. Some researchers have suggested that the ozone layer was severely damaged, bathing the land surface in ultraviolet radiation, intense enough to cause widespread mutations and reproductive failure. Scientists call it the Great Dying, which is not a nickname designed to help you sleep, but it is accurate. Life on Earth came closer to total annihilation during the Permian extinction than at any other point in its history, including the more famous asteroid impact that killed the dinosaurs 66 million years ago. The dinosaur extinction was dramatic and sudden, a single bad day caused by a rock from space. The Permian extinction was slower, messier, and more thorough. It unfolded over a period that may have lasted tens of thousands of years, though scholars still argue about the exact duration, and it left the planet so biologically impoverished that it took roughly 10 million years for ecosystem diversity to recover to pre-extinction levels. The primary cause, according to the current scientific consensus, was massive volcanism in what is now Siberia. A geological formation called the Siberian Traps erupted over an area roughly the size of Western Europe, pouring out millions of cubic kilometers of basalt lava and releasing enormous quantities of carbon dioxide, sulfur dioxide, and other gases into the atmosphere. The eruptions may have also ignited vast coal deposits and organic-rich sediments in the surrounding crust, adding even more carbon to the atmosphere and triggering runaway greenhouse warming. The details are still debated, because 252 million years is a long time and the evidence is fragmentary, but the broad picture is well established. The Siberian Traps broke the planet's climate, poisoned the oceans, and killed almost everything. Now imagine, just for a moment, that somewhere in the late Permian world, before the eruptions began, a civilization existed, not necessarily human-like. Perhaps descended from the synapsids, the group of reptile-like animals that were the dominant large land animals of the Permian and that would eventually give rise to mammals. Synapsids included a wide range of forms, some large, some small, some herbivorous, some predatory, and they had already been evolving for over 100 million years by the late Permian. Some of the later synapsids, the cynodonts, show features that suggest increasing metabolic activity, more complex teeth, possibly warm-bloodedness, and brain-to-body ratios that were high for their time. Nobody is claiming cynodonts were building cities, but you are playing the long game tonight, and 100 million years of evolution is a lot of time for a lineage to experiment with intelligence. If such a civilization had existed in the late Permian, the Great Dying would have erased it more thoroughly than any other mechanism you've discussed tonight. Not just through the usual processes of erosion and chemical degradation, but through outright destruction. The Siberian traps did not just change the climate, they physically resurfaced vast areas of the northern hemisphere with fresh lava. They burned forests across entire continents. They acidified the oceans so severely that carbonate shells dissolved. The environmental conditions during the extinction were so extreme that they would have accelerated the decay and destruction of any artificial materials, any chemical signatures, any isotopic anomalies that a pre-existing civilization might have left behind. It is like trying to find evidence of a sand castle after a tsunami. The wave does not just knock the castle down, it rearranges the entire beach. And here is the detail that makes the Permian extinction particularly effective as an evidence eraser. The recovery period that followed was so long and so complete that the ecosystems that eventually replaced the Permian world bore almost no resemblance to what came before. The dominant animal groups changed entirely. The dominant plant communities changed. The chemistry of the oceans changed. The world that emerged from the Great Dying was, for all practical purposes, a new planet built on the ashes of the old one. If you were a geologist studying post-extinction rocks, you would have very little context for interpreting any anomalies you found in pre-extinction layers, because the two worlds are so different that comparison is almost meaningless. There is a quirky and somewhat chilling analogy that one geologist offered. The Permian extinction is like a fire that burned down a library, and the Triassic recovery is like someone building a new library on the same spot with completely different books. You can study the new library all you want, but it tells you nothing about what was in the old one. The ashes are beneath the foundation, compressed and chemically altered, and mixed with the rubble of a world you cannot reconstruct. You pull the blanket closer and feel the weight of 252 million years pressing gently on your chest. Somewhere beneath the Siberian plains, beneath layers of basalt and sediment and time, the ashes of the Permian world keep whatever secrets they were given. And you are beginning to understand that some secrets are not hidden. They are destroyed, completely, irreversibly, and without apology. The ashes settle, and the world rebuilds, and now you are walking into the long, warm, reptile-dominated afternoon of the Mesozoic era. The Great Dying has cleared the stage, and the creatures stepping into the spotlight are the ones you've been waiting for all evening, even if you did not know it yet. The dinosaurs. And the question hanging in the humid Mesozoic air is deceptively simple. If any group of animals ever had enough time to produce intelligence, was it not these? Dinosaurs dominated the planet for roughly 165 million years. You need to sit with that number for a moment, because your brain will try to skip past it the way it skips past all large numbers, converting it into a vague sense of a long time and moving on. So, anchor it. Modern humans, the species that invented agriculture and writing and nuclear weapons and reality television, have existed for about 300,000 years. The genus Homo, including all the earlier human-like species, stretches back maybe 2 to 3 million years. Dinosaurs were the dominant land animals for a span roughly 55 to 80 times longer than the entire existence of the human genus. If you compressed dinosaur dominance into a single calendar year, the entire history of the Homo lineage would fit into the last 4 days. Recorded human civilization would begin about 45 minutes before midnight on December 31st. That is an almost obscene amount of time, and during that time dinosaurs were not standing still. They were evolving constantly, diversifying into thousands of species, adapting to every terrestrial environment from polar forests to tropical deserts. They ranged in size from sparrow-sized feathered creatures to the largest land animals that have ever existed. They developed complex social behaviours, parental care, herding strategies, and in some lineages, brains that were surprisingly large relative to their body size. Which brings you to the animal that makes this whole thought experiment uncomfortably plausible: Troodon. It was a small bipedal carnivorous dinosaur that lived during the late Cretaceous period, roughly 77 million years ago. Troodon was about 2 meters long, weighed maybe 50 kilograms, stood upright on 2 legs, and had forward-facing eyes that gave it stereoscopic vision. But the feature that caught the attention of paleontologists was its brain. Relative to its body size, Troodon had one of the largest brains of any known dinosaur, comparable in its encephalization quotient to some modern birds, which are themselves the living descendants of dinosaurs, and include some of the most intelligent animals on the planet. In 1982, a paleontologist named Dale Russell published a thought experiment that has been generating arguments and uncomfortable silences at academic conferences ever since. Russell asked a straightforward question: what if the asteroid had not hit? What if the Cretaceous had continued for another few million years, and the Troodon lineage had kept evolving along its existing trajectory of increasing brain size, bipedal posture, and manipulative forelimbs? Where might that trajectory have led? Russell went so far as to create a speculative model of what he called a dinosauroid, a hypothetical descendant of Troodon that had evolved human-like intelligence. His model was bipedal, large-brained, had dexterous hands with opposable digits, and looked disturbingly like a green, scaly human. The scientific community had mixed reactions, to put it diplomatically. Some researchers praised the thought experiment as a creative exploration of evolutionary possibilities. Others criticized it for being too anthropocentric, for assuming that intelligence must inevitably converge on a humanoid body plan. Scholars still argue about whether Russell's dinosauroid represents a legitimate extrapolation of evolutionary trends or an exercise in projecting human anatomy onto a reptilian canvas. But beneath the debate about the dinosauroid's appearance lies a more serious question that even the critics take seriously. Was the Troodon lineage, or some other lineage of small, brainy, socially complex dinosaurs, on a trajectory toward higher intelligence? And if so, how far along that trajectory might they have gotten during the tens of millions of years they had available before the asteroid ended the experiment? Here is a genuinely unsettling piece of arithmetic. Troodon lived about 77 million years ago, but dinosaurs had already been around for over 100 million years before Troodon appeared. The early dinosaurs of the Triassic were small, relatively simple creatures. Over the course of the Jurassic and Cretaceous, multiple dinosaur lineages independently evolved larger brains, more complex behaviours, and more sophisticated sensory systems. This is convergent evolution again, the same pattern you saw with octopuses and crows, the universe returning to intelligence as a solution whenever the opportunity arises. If the trend toward bigger brains and more complex behaviour was already underway in multiple dinosaur lineages, it is not unreasonable to wonder whether some lineage, somewhere, at some point during that vast 165 million year window, might have crossed a threshold. Not necessarily Trudon. Maybe a lineage you have never heard of because it lived in an environment hostile to fossilization. Maybe a small, social, forest-dwelling species that built with wood and plant fibre and left nothing behind. Remember that the fossil record of small terrestrial animals is far patchier than the record of large ones, because large bones are easier to find and more resistant to destruction. The clever little dinosaurs, the ones most likely to have been on the intelligence fast track, are exactly the ones least likely to be preserved. There is a quirky detail worth savouring here. Modern birds, the only surviving dinosaurs, include species like the New Caledonian crow, which manufactures and uses tools in the wild, and the African grey parrot, which can learn hundreds of words and use them in contextually appropriate ways. These are living dinosaurs demonstrating complex cognition right now, today, in your world. They are proof that the dinosaur body plan is compatible with intelligence. The hardware works. The question is just whether any dinosaur lineage had enough time and the right evolutionary pressures to push that hardware further. 165 million patient years. You let the number wash over you like warm water, and somewhere in those years, in a forest that no longer exists, on a continent that has since drifted to a different latitude, something with bright eyes and clever hands might have looked up at the stars and wondered. Those bright eyes and clever hands, if they ever existed, faced one final enemy that no amount of intelligence could outsmart. Not an asteroid, not a volcanic eruption, not even the slow grinding of erosion and chemical decay. Something far more thorough, far more patient, and far more absolute. The planet itself, eating its own surface and recycling it into fresh rock, over and over, in an endless loop that has been running for billions of years. You're thinking about plate tectonics now, and you're beginning to understand why it might be the single greatest obstacle to ever confirming or denying the Silurian hypothesis. Because plate tectonics does not just move continents around like furniture in a slow-motion living room, it actively destroys the geological record, swallowing entire stretches of Earth's history into the mantle and replacing them with blank, pristine basalt that remembers nothing. Here is how it works, in the gentlest terms your sleepy mind can handle. The Earth's outer shell, the lithosphere, is broken into a series of rigid plates that float on the semi-fluid asthenosphere beneath them. These plates move, driven by convection currents in the mantle, at roughly the speed your fingernails grow. A few centimetres per year, imperceptible on a human timescale, but devastating over geological time. Where plates pull apart at mid-ocean ridges, new crust is created as magma wells up from below and solidifies. Where plates collide, one plate is forced beneath the other in a process called subduction, and the descending plate is dragged down into the mantle, heated, melted and recycled into the planet's interior. The ocean floor is the primary victim of this process. New oceanic crust is constantly being created at mid-ocean ridges and constantly being destroyed at subduction zones. The average lifespan of oceanic crust is roughly 200 million years. That means no ocean floor on Earth today is older than about 200 million years. Everything older has been subducted, melted, and stirred back into the mantle. Gone, not buried, not hidden, unmade. Let that sink in for a moment, because the implications are enormous. 200 million years is the hard limit for any evidence that was ever deposited on the ocean floor. And since roughly 70% of the Earth's surface is ocean, that means roughly 70% of the planet's surface has been completely replaced, at least once since the early Jurassic. Any civilization that existed before that cutoff and left its traces on ocean-adjacent land or on the seafloor itself has had its evidence literally consumed by the planet. And it gets worse. continental crust is more durable than oceanic crust. It is thicker, lighter, and more buoyant, so it resists subduction. Some continental rocks are billions of years old, but continental crust is not immune to destruction. It gets folded, faulted, metamorphosed, and eroded. Mountain-building events compress and heat rocks so severely that their original features are obliterated. Erosion wears down exposed surfaces and carries sediment into the oceans, where it is eventually subducted. The oldest continental rocks that survive are heavily metamorphosed, meaning they have been so altered by heat and pressure that their original character is unrecognizable. Trying to find evidence of a civilization in a 3 billion-year-old metamorphic gneiss is like trying to read a letter that has been fed through a furnace. The paper is still there, technically, but the words are gone. Scholars still argue about exactly how much of Earth's original continental crust has survived to the present day. Estimates vary, but some geologists believe that a significant fraction of the crust that existed more than 1 billion years ago has been recycled through erosion and subduction. The surviving ancient rocks are scattered, isolated remnants, tiny windows into a past that has been mostly closed. Now remember that crocodile dung sunscreen analogy from earlier. Wait, you have not encountered that one yet, so never mind, but the point stands. The planet is not a museum. It is a recycling plant. It takes its old surfaces, breaks them down, melts them, and uses the raw materials to build new surfaces, and it has been doing this for over 4 billion years. Any evidence that was once on those surfaces, fossils, chemical signatures, artifacts, anomalous isotope ratios, goes into the recycler along with everything else. This is particularly devastating for the Silurian hypothesis because civilizations, at least the ones you know about, tend to concentrate along coastlines. Humans build cities near water, ports, harbours, fishing villages, coastal trade routes. These are the foundations of most human civilizations. If a pre-human civilization followed a similar pattern, and there are good ecological reasons to think it might have, since coastlines are biologically productive environments that provide abundant food and transportation routes, then its densest concentration of evidence would have been on or near the ocean floor. And the ocean floor older than 200 million years does not exist anymore. It has been subducted. Every trace, every foundation stone, every chemical fingerprint, pulled into the mantle and melted into magma that will eventually emerge as fresh basalt at a mid-ocean ridge, innocent and blank and carrying no memory of what it once was. There's a beautifully frustrating irony here. The same geological processes that make Earth habitable, plate tectonics, drives the carbon cycle, regulates the climate, builds mountains that create diverse habitats, are also the processes that make Earth's history unreadable. You live on a planet that is perfect for producing civilizations and terrible for remembering them. It is as if the universe designed a stage that was ideal for performances, but compulsively scrubbed clean between acts. You feel the ground beneath you differently now, not as something solid and permanent, but as something in motion, something alive, something hungry. The tectonic plates shift a few centimeters while you lie here, carrying you imperceptibly toward a future that will eventually erase all evidence that you were ever here, just as it may have erased everything that came before. The ground moves beneath you, slow and hungry, and now you flip the whole question on its head like a pancake that has been cooking too long on one side. You have spent the last several sections asking whether a pre-human civilization could have left detectable traces. Now you ask the opposite. If your civilization, the one that built the phone you might be holding right now, vanished tonight, every human gone in an instant, what would be left after 1 million years, after 10 million, after 100 million? How long before the Earth forgets you entirely? This is not a morbid exercise. It is the most useful thought experiment available for understanding the Silurian Hypothesis, because it gives you a control case. You know exactly what your civilization has built, how much of it there is, and what materials it is made of. So you can trace the decay curve with some confidence, and find out just how quickly the most prolific civilization in Earth's known history would become invisible. The early stages of erasure are almost insultingly fast. Within days of human disappearance, power grids fail, and the pumps that keep subways and basements dry shut off. Water begins reclaiming underground infrastructure immediately. Within weeks, pets that survived the initial confusion have gone feral and begun reshaping urban ecosystems. Within a year, vegetation is cracking through asphalt and climbing the walls of buildings. The roots of trees and shrubs are patient, relentless demolition crews, and they work for free. Within 20 years, most residential structures in humid climates have suffered serious structural damage from water infiltration, mold, freeze-thaw cycling, and biological colonization. Wooden-framed houses are collapsing. Steel-reinforced concrete is cracking as embedded rebar rusts and expands. Windows have shattered from thermal stress and storm damage, allowing weather inside. The neat rectangles of suburban neighborhoods are becoming meadows studded with rubble. Within 100 years, most bridges have failed. Dams are silting up and overtopping. Wooden structures are gone entirely. Even stone and masonry buildings are deteriorating as mortar dissolves and individual stones shift and tumble. The great cities are forests now, their streets converted to streams, their plazas converted to clearings where deer graze and hawks circle. You would still recognize the outlines if you flew overhead, the grid pattern of former streets, the foundations of skyscrapers poking up through the canopy. But the outlines are fading. Within 1,000 years, most above-ground structures have been reduced to rubble mounds. A few exceptionally durable monuments survive. The Great Pyramids of Giza, certain massive stone fortifications, the carved faces of Mount Rushmore, though all are heavily weathered and crumbling. The Mount Rushmore faces, which were carved into relatively soft granite, would be eroded beyond recognition within about 75,000 years according to some geological estimates. The pyramids might last longer, perhaps a few 100,000 years, but even they are not forever. They are just slow. Within 10,000 years, the last visible structures are low mounds of rubble overgrown with soil and vegetation. Archaeologists from some future intelligent species might still identify them as the artificial if they knew what to look for, but without prior knowledge, they would be easy to mistake for natural formations. Many ancient human structures from just a few thousand years ago are discovered only by accident when a farmer's plough catches on something unexpected or satellite imagery reveals crop marks caused by buried foundations affecting plant growth, and those are structures only a few millennia old. Scale to 10,000 years and the subtlety increases enormously. Within 100,000 years, the physical footprint of human civilization on the surface is essentially gone. Ice ages have come and gone. Glaciers have bulldozed across former cities in the northern hemisphere, grinding the rubble to gravel and spreading it across the landscape in moraines. River courses have shifted, burying some areas under fresh sediment and exposing others to erosion. The geographical features you associate with your civilization, harbours, canals, levees, terraced hillsides, have been reshaped beyond recognition by natural processes. But underground, things last a little longer. Landfills, those vast burial mounds of compressed garbage, would persist as unusual geological formations for perhaps 1 million years or more. The mix of materials in a landfill, plastic fragments, metal oxides, glass shards, synthetic chemicals, ceramic pieces, is unlike anything that occurs naturally. and a future geologist drilling through one would find a bizarre layer of mixed artificial materials compressed between ordinary sediment layers. Scholars still argue about how long the chemical signature of a landfill would remain distinguishable from background geology, but most estimates suggest that after 10 million years the organic components have decomposed entirely, and the inorganic components have been chemically altered to the point of ambiguity. And what about the chemical signatures you discussed earlier? The carbon isotope excursion from burning fossil fuels, the nitrogen anomalies from agriculture, the trace metal spikes from industry. These would be your most durable legacy, compressed into a thin but distinctive layer in ocean sediments and continental deposits. The carbon spike alone, representing roughly 3 centuries of intensive fossil fuel burning, would show up as a sharp negative excursion in the carbon-13 record, similar in character though different in duration from the PETM event you explored a few sections ago. That spike might remain detectable for tens of millions of years, though it would become increasingly difficult to distinguish from natural carbon excursions as the signal degraded and the surrounding chemical context was lost. There is a quirky and slightly depressing detail worth mentioning. The single most durable artifact of human civilization might turn out to be not a monument or a building or a time capsule, but the layer of radioactive isotopes deposited in sediments worldwide by nuclear weapons testing in the mid-20th century. Certain isotopes, like plutonium-239, have half-lives of 24,000 years and do not occur naturally in significant quantities. That faint radioactive signature in the sediment might be the last whisper of your entire species, detectable for a few 100,000 years before it too fades into the background. You lie there and feel the gentle weight of your own impermanence. Everything you have built, everything you know, everything you are, reduced to a thin smear of unusual chemistry in a layer of mud. And if that is what happens to you with all your concrete and steel and plastic and nuclear waste, imagine what happened to something that came before, something that built with gentler materials in a world that has since been recycled a dozen times over. That thin smear of unusual chemistry is still settling in your mind as you turn your attention to something that has probably been nagging at you for a while. What about the weird stuff? The artifacts that seem to be in the wrong place at the wrong time. The objects that pop up in breathless internet articles with titles like "Scientists can't explain this ancient discovery," followed by 17 exclamation points and an advertisement for weight loss supplements. You've been patient and scientific all evening, and now you are going to wade into the murky waters of anomalous artifacts, because the Silurian Hypothesis would be incomplete without at least glancing at the things people have actually claimed to find. Let us start with the honest disclaimer. The vast majority of so-called out-of-place artifacts, sometimes abbreviated as OOP arts by people who enjoy acronyms, are not genuinely anomalous. They are misidentified, misunderstood, poorly documented, or outright fabricated. The history of anomalous artifact claims is littered with hoaxes, honest mistakes, and wishful thinking, and taking any individual claim at face value without rigorous investigation is a fast track to embarrassment. That said, sorting through the mess is instructive, because it teaches you what a genuine anomaly would need to look like in order to be taken seriously. Consider the London hammer, one of the most frequently cited OOP arts. It is an iron hammer with a wooden handle that was reportedly found embedded in a rock formation in London, Texas, in the 1930s. Proponents claim the rock is hundreds of millions of years old, which would make the hammer impossibly ancient. The reality is considerably less exciting. Geologists who have examined the specimen point out that the rock surrounding the hammer is not part of the native geological formation. It is a concretion, a mass of calcium carbonate that precipitated around the hammer after it was dropped or discarded, probably in the 19th century. Minerals can form concretions around objects relatively quickly under the right chemical conditions, sometimes within decades. The hammer is almost certainly an ordinary 19th century mining tool that got cemented into a lump of calcium carbonate and was later found by someone who assumed the surrounding rock was ancient. Case closed, though the hammer continues to reside in a creationist museum in Texas, where it is displayed with considerably less geological nuance. Then there is the Antikythera mechanism, which is genuinely extraordinary but not anomalous in the way this conversation requires. Discovered in a Roman-era shipwreck off the coast of the Greek island Antikythera in 1901, it is a complex bronze gearwork device dating to roughly the 2nd century BCE. It was used to predict astronomical positions, eclipses, and possibly calendar cycles, and its sophistication stunned researchers who did not expect that level of mechanical engineering from the ancient Greek world. Scholars still argue about exactly who built it and how widespread such devices might have been. But the Antikythera mechanism is not evidence of a pre-human civilization. It is evidence that ancient humans were cleverer than modern humans sometimes give them credit for, which is a different and arguably more interesting lesson. What about the Klerksdorp spheres, those small grooved metallic balls found in 3-billion-year-old rock in South Africa? They look manufactured, with regular grooves and surprisingly uniform shapes, and they have fueled speculation about ancient intelligent design. Geologists, however, identify them as natural concretions formed by the precipitation of minerals in volcanic sediments. Similar natural spheres form in various geological settings around the world. They look artificial to the untrained eye because human brains are pattern recognition machines that see intentional design everywhere, even in the output of purely geological processes. You see a face in the moon, a bunny in the clouds, and a manufactured object in a natural mineral concretion. Your brain is helpful like that, and also wrong quite often. The list goes on. Ancient spark plugs supposedly embedded in 500,000-year-old rock, actually a 1920s champion spark plug encased in a natural concretion. Iron pillars that never rust. Actually, they do rust, just very slowly due to their specific alloy composition and the local climate. Stone walls discovered on the ocean floor, actually natural rock formations with regular joint patterns caused by geological fracturing. For every claimed anomaly, there is a mundane explanation supported by evidence, and the mundane explanation is almost always correct. But here is the thing, and it connects back to everything you've been learning tonight. The fact that all known P-arts have been explained does not tell you what a genuine anomaly would look like if one were ever found. And that question is worth taking seriously, because if you are going to search for evidence of a pre-human civilization, you need to know what you are looking for. A genuine out-of-place artifact would need to meet several criteria simultaneously. First, it would need to be found in a geological context that is unambiguously ancient, not in a concretion or a disturbed layer, but in undisturbed sedimentary rock whose age can be independently verified. Second, the artifact itself would need to be made of materials or possess a structure that cannot be produced by any known natural process. Not just unusual, but definitively artificial. Third, the discovery would need to be documented with rigorous chain of custody procedures, photographed in situ before removal, and examined by multiple independent laboratories. Fourth, and this is the hardest criterion, all plausible natural explanations would need to be systematically eliminated. No claimed OOP art has ever met all four criteria, not one, and that is telling. It suggests either that pre-human civilizations never existed, which is the simplest explanation, or that their artifacts have been so thoroughly destroyed by deep time that nothing recognizable has survived to be found, which is the possibility that keeps the Silurian Hypothesis alive. There is a quirky irony in all of this. The people who most eagerly promote anomalous artifacts, the conspiracy theorists and ancient mystery enthusiasts, are actually undermining the search for genuine evidence by flooding the field with noise. Every debunked OOP art makes scientists more skeptical of the next claim, more likely to dismiss anomalies without thorough investigation, more certain that the whole enterprise is pseudoscience. The hoaxes and mistakes create a boy who cried wolf effect that could, in theory, cause a real anomaly to be overlooked. You smile faintly in the dark because the universe has a sense of humour about these things. The truth, if it is out there, might be hiding not just beneath millions of years of rock, but behind a wall of bad television documentaries and clickbait headlines. And that is a different kind of burial altogether. You're smiling at the irony, and now your mind drifts naturally toward a more productive question. If you were serious about looking for evidence of a pre-human civilization, not collecting dubious hammers from Texas gift shops, but genuinely searching with a full toolkit of modern science, where would you look? What locations on or off this planet might still hold traces that even deep time and plate tectonics could not completely erase? The first and perhaps most surprising answer is desert glass. Scattered across certain arid regions of the world, you can find patches of natural glass formed when intense heat melted surface sand into smooth, translucent sheets. The most famous example is Libyan desert glass, found in the sand seas along the border of Egypt and Libya. These pale yellow-green fragments are roughly 29 million years old and are stunningly beautiful. So beautiful that a carved scarab made from Libyan desert glass was found among the treasures in Tutankhamun's tomb, meaning this stuff was considered precious even 4,000 years ago. The mainstream explanation for Libyan desert glass is an airburst or impact event, a comet or asteroid that exploded in the atmosphere or struck the surface with enough energy to melt the underlying sand into glass. Similar glass fields have been found in other desert regions, and most are associated with known or suspected impact events. But here is the detail that makes glass fields interesting for tonight's question. Nuclear weapons tests in the mid-20th century also produced glass. The first atomic bomb test at Trinity Site in New Mexico created a thin sheet of green glass called trinitite, formed when the nuclear fireball melted the desert sand. Trinitite and Libyan desert glass are chemically different because they formed under different conditions, but the principle is the same. Extreme heat plus sand equals glass. Nobody credible is suggesting that Libyan desert glass was produced by ancient nuclear weapons. The impact hypothesis is well supported and far more parsimonious, but the existence of these glass fields demonstrates that certain types of high-energy events leave durable traces in desert environments, and if you wanted to search for anomalous heat events in the deep past, desert glass deposits would be a reasonable place to start. Scholars still argue about the exact formation mechanism of some glass fields, because the temperatures required to produce certain varieties seem higher than what standard impact models predict, and the distribution patterns of some deposits do not quite match the expected dispersal from a single impact point. These are minor technical debates, not evidence of ancient civilizations, but they illustrate that even well-studied geological phenomena can harbour unresolved questions. The second place you would look is the Moon. This might seem like a strange suggestion, until you remember what makes the Moon so special from a preservation standpoint. The Moon has no atmosphere, no weather, no liquid water, no plate tectonics, and no biological activity. It is, geologically speaking, dead. Objects placed on the lunar surface stay there essentially forever, disturbed only by the occasional micrometeorite impact and the slow degradation of solar radiation. The footprints left by Apollo astronauts in 1969 are still there, perfectly preserved in the fine lunar regolith, and they will remain visible for millions of years. If a pre-human civilization had achieved spaceflight and visited the moon, any artifacts left behind would still be sitting on the surface, waiting. This is not as far-fetched as it sounds, provided you are willing to imagine a civilization that existed for long enough to develop advanced technology, which, as you have already discussed, is a big if, but not an impossible one. Several scientists have semi-seriously proposed that a systematic photographic survey of the lunar surface at high resolution could search for anomalous objects or structures. The Lunar Reconnaissance Orbiter, which has been mapping the moon since 2009, has photographed the surface at resolutions high enough to spot the Apollo landing sites and the tracks left by astronauts' boots. If something artificial and reasonably large was sitting on the lunar surface, the imagery might already contain it, buried in terabytes of data that nobody has examined pixel by pixel. There is a wonderfully quirky detail here. In 1993, a researcher named Alexei Arkhipov published a paper suggesting that even if a pre-human lunar artifact were photographed, it might be dismissed as a rock or a natural formation unless someone specifically looked for it. The human brain is excellent at seeing patterns where none exist, as you learned with the Klerksdorp spheres, but it is also surprisingly good at not seeing things that do not match its expectations. If you are scanning thousands of lunar photographs looking for geological features, your brain filters out anything that does not look geological. A small artificial structure might register as an oddly shaped boulder and never get a second glance. The third and most accessible place to look is deep ocean sediment cores. The ocean floor gets recycled every 200 million years, as you learned when you wrestled with plate tectonics, but the sediment that accumulates on top of that floor is a layered chemical diary that records atmospheric and oceanic conditions stretching back millions of years. Scientists routinely drill these cores to study past climates, and the data they contain is extraordinarily detailed. A systematic reanalysis of existing sediment cores, specifically searching for the chemical signatures that Schmidt and Frank identified, anomalous carbon isotope excursions, synthetic molecule traces, unusual concentrations of industrial metals, could potentially reveal signals that were previously overlooked because nobody was looking for them. This is perhaps the most practical recommendation to emerge from the Silurian Hypothesis. You do not need a time machine or a moon mission. You need a geochemist, a mass spectrometer, and a willingness to ask strange questions of data that has already been collected. The evidence, if it exists, might already be sitting in a university freezer somewhere, locked in a cylinder of ancient mud, waiting for someone to analyse it with the right question in mind. You settle deeper into your pillow and let the image form. A laboratory, quiet and fluorescent lit. A cylinder of grey sediment sliced thin as paper. A scientist squinting at a graph that shows a tiny, unexplained spike in a line that should be smooth. A moment of hesitation. A penciled note in a margin. And then, maybe the beginning of a very different conversation. That penciled note in the margin stays with you, and now your sleepy mind begins to wander upward, away from the mud cores and the moon dust and the desert glass, toward the stars. Because the question you have been circling all evening does not belong to geology alone. It belongs to the biggest, loneliest, most humbling question in all of science. Are we alone? And if the answer is no, the explanation might not be out there in the galaxy at all. It might be right here, buried in the dirt, separated from you not by light years but by millions of years. This is where the Silurian Hypothesis and the Fermi Paradox shake hands and sit down for an uncomfortable conversation. You have probably heard of the Fermi Paradox, even if you have not called it by name. It is named after the physicist Enrico Fermi, who reportedly asked during a lunch conversation in 1950 a question so simple and so devastating that it has haunted astronomers ever since. The question, paraphrased, was this: If the universe is so vast and so old and so full of stars and planets, where is everybody? Given the billions of galaxies, each containing billions of stars, many with planets in habitable zones, and given that the universe is nearly 14 billion years old, plenty of time for intelligent life to arise and spread, you would expect the cosmos to be teeming with civilizations. You would expect to see their signals, their megastructures, their spacecraft, their colonization efforts. And yet you see nothing. The sky is silent. The radio waves carry only noise. The telescope images show only stars and gas and dust, and the profound, echoing emptiness of a universe that appears, against all statistical probability, to be unoccupied. The Fermi paradox has generated dozens of proposed solutions over the decades, each more creative and more unsettling than the last. Maybe intelligent civilizations destroy themselves before they can spread beyond their home planet through nuclear war or ecological collapse or some technology so powerful it becomes self-annihilating. This is the idea of the Great Filter, a hypothetical barrier that prevents civilizations from reaching a spacefaring stage. Maybe civilizations deliberately hide, going silent to avoid detection by predatory species that roam the galaxy, looking for competitors to eliminate. This is the dark forest hypothesis, popularized by the Chinese science fiction writer Liu Cixin, and it is exactly as cheerful as it sounds. Maybe the distances between stars are simply too vast for any civilization to cross, no matter how advanced, and the galaxy is full of intelligent species all marooned on their individual worlds, shouting into the void and hearing nothing back. But here is the solution that connects directly to everything you have been lying here thinking about. Maybe the Great Filter is not ahead of us. Maybe it is behind us. Maybe it has already happened on this very planet multiple times. Imagine that intelligence is not rare in the universe but fragile. It arises periodically on planets that meet the right conditions, flourishes for a geological eye blink, and then collapses either through self-destruction, environmental catastrophe, or some combination of both. The civilization leaves a brief chemical smudge in the sediment, a thin layer of isotopic anomalies that fades over millions of years, and then the planet moves on. New species evolve, new ecosystems form, and eventually, given enough time, intelligence arises again, and again, and again. Each iteration ignorant of its predecessors, each believing itself to be the first, each destined to leave only the faintest trace before the cycle repeats. This is a deeply unsettling vision, and scholars still argue about whether it is legitimate scientific hypothesis or a philosophical mood dressed up in technical language. But it has the uncomfortable virtue of being consistent with the evidence. You have already seen how thoroughly the Earth erases its history. You have already learned that the chemical signature of a civilization would be indistinguishable from certain natural events after enough time. You have already accepted that the fossil record is more gap than story. If civilizations are cyclical, rising and falling like waves on a very slow ocean, the geological record might not be able to tell you, and the Fermi paradox itself becomes less paradoxical in this framework. The reason you do not see alien civilizations might not be that they never existed. It might be that they existed briefly, repeatedly, on planets all over the galaxy, and each one vanished before it could spread to the stars. The universe is not empty. It is full of graveyards that do not look like graveyards, because the headstones have eroded and the names have been forgotten. There is a quirky and somewhat poetic extension of this idea that a few thinkers have explored. What if intelligence is the planet's way of processing a crisis? Some researchers have noted that periods of rapid evolutionary innovation often follow mass extinctions, as if the biosphere responds to catastrophic disruption by experimenting more aggressively, producing new forms and new strategies at an accelerated rate. What if intelligence is one of those strategies, a tool the biosphere deploys when conditions demand rapid adaptation, and then discards when the crisis passes? In this view, you're not the pinnacle of evolution. You're a temporary emergency measure, a biological fire extinguisher that the planet pulls off the wall when things get bad and puts back when things stabilise. That is not a mainstream scientific position. It borders on teleological thinking, the idea that nature has purposes which most biologists reject. But it is a delicious thought to hold in the dark, because it reframes your entire existence as something both important and provisional. You matter, but you might not last. You're extraordinary, but you might not be unique. And the silence of the cosmos might not be silence at all. It might be the sound of a universe that has heard this story many times before and already knows how it ends. You breathe slowly, the fan turns, and the stars above the ceiling shine on worlds that might be keeping the same kinds of secrets that your own world keeps beneath its patient, recycling crust. The stars shine and the secrets keep, and now you find yourself sitting with something that is not quite a thought, and not quite a feeling, but something in between, a kind of vertigo. Not the physical kind, where the room spins and you grab for the nearest solid object, but a deeper, quieter kind. The philosophical kind. The kind that comes when you stare too long into a question that has no bottom, and realise that the ground you've been standing on your whole life might not be as solid as you assumed. Because here is what the Silurian Hypothesis really does, beneath all the chemistry and the isotope curves and the sediment cores. It takes one of humanity's most cherished beliefs, the belief that we are special, that we are first, that we are the point of the whole 4.5 billion year story, and it holds that belief up to the light and asks very politely, what if you are wrong? Human exceptionalism is not a modern invention. It is one of the oldest ideas in your species' intellectual history. Almost every culture that has ever existed placed humans at the centre of creation, either as the chosen children of gods, the pinnacle of a great chain of being, or the inevitable endpoint of evolutionary progress. Even secular modern thinking, which officially rejects the idea that evolution has a direction or a goal, still tends to treat human intelligence as something extraordinary, a qualitative leap beyond anything that came before, a cosmic jackpot that happened exactly once on this unremarkable planet orbiting an unremarkable star. And maybe it is extraordinary. Maybe you really are a one-time miracle, the only self-aware beings this planet has ever produced. That is a perfectly defensible position, and most scientists hold it because the evidence, such as it is, supports it. But the Silurian Hypothesis gently points out that the evidence is not as strong as you might like it to be. The absence of proof is being treated as proof of absence, which is a logical fallacy that would get you a stern look from any first-year philosophy student. You have not found evidence of a prior civilization, but you have also not conducted a systematic search for one using the specific tools and criteria that such a search would require. You have not, in any rigorous sense, actually looked. This is where the emotional weight of the question starts to press down, because if you take the possibility seriously, even provisionally, even as a thought experiment, it changes how you see yourself. You're no longer the protagonist of a story that was written just for you. You're a chapter, possibly a footnote, in a much longer narrative that you cannot read because the earlier pages have been dissolved by time and swallowed by geology. Your monuments, your achievements, your entire civilization might be the latest in a series of experiments that the planet has been running for hundreds of millions of years, each one believing it was the first, each one wrong. Scholars still argue about whether this kind of radical humility is psychologically healthy or psychologically corrosive. Some philosophers and scientists embrace it as a necessary corrective to anthropocentric arrogance. Knowing that you might not be special, they argue, makes you more careful, more humble, more willing to treat the planet and its other inhabitants with respect. If you are not the first intelligence, you might not be the last, and that creates a sense of responsibility toward the future that simple exceptionalism does not provide. Other thinkers push back, arguing that undermining human specialness too aggressively leads to nihilism and despair. If nothing you build lasts, if your entire civilization is destined to become a thin chemical smear in a layer of rock, why bother building anything at all? The answer, if you want one at 2 a.m. while the fan hums and the darkness wraps around you, is that impermanence does not equal meaninglessness. A sunset is beautiful precisely because it does not last. A conversation matters even though the sound waves dissipate the moment the words are spoken. Your civilization might eventually be erased, but the experience of it, the art, the love, the curiosity, the midnight conversations about whether you're alone in deep time, those things matter while they are happening. Meaning does not require permanence, it just requires attention. There is a quirky parallel in Buddhist philosophy that feels relevant here, even though you're not trying to turn this into a meditation session. The concept of impermanence, anicca in Pali, is one of the foundational teachings of Buddhism. Everything that arises eventually passes away. Clinging to the idea that things will last forever is a source of suffering. Accepting impermanence is a source of freedom. A Buddhist monk listening to this video might nod gently and say yes. Of course your civilization will be erased, just as every sand castle is erased by the tide, and the appropriate response is not grief but gratitude for the castle while it stands. And there is a resistance to this idea that is worth acknowledging honestly. Some scientists resist the Silurian hypothesis, not because the logic is flawed, but because the implications are uncomfortable. If you have spent your career studying human evolution and human uniqueness, the suggestion that humans might not be the first intelligent species is professionally threatening. It does not just challenge a hypothesis, it challenges an identity. The identity of humanity as the crowning achievement of terrestrial evolution, the one species that transcended biology and reshaped the planet according to its will. Letting go of that identity, even partially, even hypothetically, takes courage. You do not need to let go of it tonight. You just need to hold it loosely, the way you hold a leaf you found on a walk, admiring its shape without squeezing so hard that it crumbles. You are special. You might also not be first. Both things can be true, and the tension between them is not a problem to be solved, but a mystery to be inhabited. The dark hums, your eyelids are heavy, and the vertigo fades slowly into something that feels less like falling and more like floating. You're floating now gently, and the question has softened around the edges the way questions do when you've been holding them long enough. The sharp urgency of wanting an answer has given way to something more comfortable, something that feels less like a puzzle demanding a solution, and more like a landscape you're content to wander through without needing to reach any particular destination. But before you drift too far, you owe yourself an honest accounting. You've spent the evening exploring a hypothesis, building a case from chemistry and geology and evolutionary biology and deep time, and now you need to stand back and look at the whole thing clearly and ask what mainstream science actually says about all of this. Not what it might say in 20 years, not what a speculative fringe hopes it will say. What it says right now, today, in the peer-reviewed journals and the university lecture halls and the laboratories where people do the patient, unglamorous work of testing ideas against reality. The honest answer is this: there is no confirmed evidence of any pre-human civilization on Earth. None. The fossil record, incomplete as it is, has produced nothing that can be unambiguously identified as the product of non-human intelligence. The chemical record, detailed as it is, contains no synthetic molecules or isotopic signatures that require an industrial explanation. The geological record, vast as it is, holds no structures or formations that cannot be accounted for by natural processes. Every anomaly that has ever been cited as potential evidence has been explained convincingly and repeatedly by conventional science. That is the baseline, and you should respect it, because science works by following evidence, not by chasing the thrill of mystery. If you let desire for an interesting answer override the actual data, you have left science and entered storytelling. And while storytelling is wonderful and necessary and is exactly what you're doing right now at 2 a.m, it is not the same thing as knowledge. But, and this is the but that keeps the whole conversation alive, the absence of evidence is genuinely not the same as evidence of absence. And in this particular case, the distinction matters more than usual. Because unlike most scientific hypotheses, the Silurian hypothesis cannot be straightforwardly falsified. You cannot prove that something did not exist tens of millions of years ago, because the very processes that would destroy the evidence are the same processes that operate on everything in the geological record. The hypothesis sits in an uncomfortable epistemic category, not supported by evidence, but also not ruled out by evidence, because the evidence itself is expected to be missing. This drives some scientists a little bit crazy, and understandably so. Science thrives on falsifiability. A hypothesis that cannot be tested, that cannot in principle be proven wrong, is a hypothesis that does not do useful work. It just sits there, untouchable, neither confirmed nor denied, occupying intellectual space without paying rent. And some researchers view the Silurian hypothesis exactly this way, as an entertaining thought experiment that contributes nothing to practical science because it generates no testable predictions. But Schmidt and Frank would disagree, and their disagreement is worth hearing. They argue that the hypothesis does generate testable predictions, just not the kind that produce a simple yes or no. The Silurian hypothesis predicts that a systematic search of sediment cores for specific chemical signatures, synthetic molecules, anomalous isotope ratios, unusual concentrations of industrial metals would either find something interesting or would establish rigorous upper bounds on what could be detected. Either outcome advances scientific knowledge. If you search and find nothing, you have not proven the hypothesis wrong, but you have demonstrated the limits of detection, which is useful. If you search and find an anomaly that resists natural explanation, you have opened a door that could lead anywhere. Scholars still argue about whether that constitutes genuine scientific progress, or just an elaborate exercise in looking busy. The debate is ongoing, collegial, and genuinely interesting, which is more than you can say for most academic disputes that happen over lukewarm coffee in conference hotel lobbies. There is a useful analogy from the history of science that illuminates the situation. Before the discovery of exoplanets, many astronomers assumed that our solar system's arrangement was typical, that most planetary systems would have small rocky planets close to their stars and gas giants farther out. When the first exoplanets were detected in the 1990s, they turned out to be hot Jupiters, massive gas giants orbiting closer to their stars than Mercury orbits our Sun. The assumption of typicality was wrong, and it was wrong because scientists had been generalizing from a sample size of 1. The Silurian hypothesis makes a similar point about civilization. You're generalizing from one example, your own, and assuming that if anything else like you had ever existed, it would have left the same kinds of traces you would leave. But you do not actually know that. And there is one more thing that keeps serious researchers from dismissing the hypothesis entirely. The practical implications for astrobiology are significant if you want to search for signs of industrial civilizations on other planets, which is increasingly a serious scientific goal. As telescope technology improves, you need to know what those signs would look like after millions or billions of years of geological processing. The Silurian hypothesis, by forcing you to think about how quickly evidence degrades, on a geologically active planet helps you build better models for detecting ancient civilizations on Mars, on Venus, on exoplanets with thick atmospheres and active surfaces. The question is not just about Earth's past. It is about how you search for intelligence anywhere. So mainstream science holds the line. No evidence found. Hypothesis unconfirmed. But the door remains open, not because scientists are credulous, but because the question is genuinely harder to answer than it looks, and the tools for answering it are still being developed. The pencil hovers over the margin. The note has not yet been written. You feel that floating sensation again. The not knowing is not uncomfortable anymore. It is spacious. It is room to wonder without needing to conclude. The room to wonder opens up around you like a sky clearing after a long overcast day, and you realise that you've been on quite a journey tonight. You started standing barefoot on ancient rock, pressing your palm against stone that predates everything you have ever known, and you have travelled through billions of years of deep time, through vanishing fossils and crumbling cities, and strange chemical whispers in layers of ancient mud. You have met giant dragonflies and clever dinosaurs and octopuses that think with their arms. You have watched Manhattan dissolve. You have stared into the Fermi paradox and felt the philosophical vertigo of maybe not being first. And now, as your breathing slows and the darkness around you grows softer and warmer, you find yourself arriving not at an answer, but at something better. A question you can hold gently, without needing to squeeze it into a shape it does not want to take. The Earth is old, you are not. And the space between those two facts is filled with a silence that might be empty, or might be full of stories you do not yet know how to read. Both possibilities are beautiful. Both are humbling. And neither one diminishes what you are or what your species has accomplished in its brief, brilliant, improbable moment on the surface of this restless, recycling, secret-keeping planet. There is something freeing about sitting with uncertainty. You live in a world that demands answers, that rewards confidence, that treats not knowing as a failure rather than a starting point. But tonight, in the dark, with the fan humming and your body heavy and warm, not knowing feels like the most honest and most courageous position available. You do not know whether something was here before you. You do not know whether the PTM was purely volcanic or whether something stranger contributed. You do not know whether a clever little dinosaur in a Cretaceous forest ever looked at the moon and wondered what it was made of. You do not know whether the octopus's eerie intelligence is a first draft or a distant echo of something older, and that not knowing is not a gap in your understanding. It is the edge of your understanding, the place where knowledge ends and wonder begins, and wonder is the thing that got you here in the first place. Remember that walking exercise from earlier tonight, 1 step per year, 70 years of non-stop walking to reach the birth of the planet. You have been walking all evening in your mind through those incomprehensible depths of time, and now you can stop. You can stand still. You can let the timeline stretch out behind you and ahead of you and feel, just for a moment, how small and how precious your position in it is. You're a creature made of stardust and water and electricity, standing on a ball of rock and iron that has been spinning through space for 4.5 billion years, and you're asking questions that the rock itself cannot answer. That is extraordinary. That might be the most extraordinary thing that has ever happened on this planet. Or it might be the latest in a long series of extraordinary things that happened and were forgotten. Either way, you're here now, and you're asking, and the asking matters. The chemical ghosts in the sediment, the isotope curves, the strange spikes and unexplained excursions, they will still be there tomorrow. The scientists with their mass spectrometers and their sediment cores and their careful, patient questions will keep working. Maybe someday someone will find the pencil note in the margin that changes everything. Maybe they will drill a core in the right place and see a spike that resists every natural explanation. Maybe a lunar orbiter will photograph something on the surface of the moon that makes everyone stop and reconsider. Or maybe not. Maybe the silence is real, and you're genuinely the first, the only, the one and only civilization this planet has ever hosted. That would be its own kind of miracle, its own kind of loneliness, its own kind of responsibility. You do not need to decide tonight. That is the gift of a question like this. It does not expire. It does not demand a verdict. It just asks you to stay curious, to hold your assumptions lightly, to remember that the universe is under no obligation to make sense to you, and that the things you do not know vastly outnumber the things you do. The fan turns, slow and steady, and the hum has become so familiar now that it feels like part of your own breathing. The darkness is not empty. It is full of time and stone and the patient silence of a planet that has seen everything and remembers almost nothing. And in that silence, you're a small warm point of awareness, a candle flame in a cathedral of deep time, flickering gently, beautifully, briefly. Let your eyes close if they have not already. Let your hands uncurl. Let the weight of 4.5 billion years settle around you, not as a burden, but as a blanket, the oldest and softest blanket imaginable, woven from starlight and geology, and the quiet turning of a world that was here long before you, and will be here long after. You are safe. You are held. You are part of something so vast and so ancient that your mind cannot contain it, and that is perfectly fine. You do not need to contain it. You just need to rest inside it, the way a shell rests on the ocean floor, the way a fossil rests in the rock, the way a question rests in the mind of someone who has learned that not every question needs an answer tonight. The stars turn slowly above the ceiling you cannot see. The earth hums beneath you, old and warm and full of secrets, and you drift, gently, gratefully, into the deep and dreamless dark, carried by the same patient currents that have carried everything else, every creature, every wonder, every civilization known and unknown, into the soft and endless night. Sweet dreams.